Question 9. This is from the Wilson Buffa College Physics book, and it's Chapter 3. An x component of a velocity vector is given as 4.8 meters per second. The angle of that component is 37 degrees to the actual velocity. So an object is being launched at some angle at some velocity, and the x component is determined to be 4.8 meters per second. The question asks what's the actual velocity, and then what's the y component of the velocity. So let's start off with, well, first of all, our math for the x component says that the velocity in the x direction is equal to the velocity times the cosine of the angle. Well, we've got the x component. We want the velocity. So the algebra says to divide the velocity in the x component by the cosine of the angle. So the velocity in the x component is 4.8 meters per second, and you divide that by the cosine of 37 degrees. And I will leave that bit to work out for you. In dimensional analysis, the units will be in meters per second. Well, if you find this velocity, the velocity in the y-axis is straightforward. Velocity in the y-axis equal to velocity times the sine of the angle. And so you could use the velocity that you found there and the angle that you were given, and you could find the velocity in the y-axis. We tend in physics to not want to use something we found if we can help it. I had to find velocity. What if I make a mistake in my math, or I round off my cosine? My velocity here isn't going to be really what I'm looking for. And so I kind of would like to use the tangent. If the tangent of the angle is equal to velocity in the y divided by the velocity in the x, then the velocity in the y is equal to the tangent of the angle times velocity in the x. I've got velocity in the x given to me, I've got angle given to me. So this is the better equation to find the velocity in the y-axis. But that's how you would do problem 9, which is the first of the level 2 problems in the book. The next problem I'm going to do would be number 33 from the textbook, Chapter 3. This is page 96. And it has a airplane flying northwest for 250 miles and then west for 150 miles. So I'm going to do this. Northwest implies, and it has to do with the compass, and the compass would be, if we had 90 degrees to each other, and this is north and south and east and west, and so the compass heading of northwest implies 45 degrees. 45 degrees would be right about there. And so it's heading in that direction, and it's told it does that at a velocity, or it does that for 250 miles. So we want to take that velocity vector and come up with some kind of a scale. So I'm going to say 1 centimeter is equal to 50 miles. So 250 miles would be equal to 5 centimeters. And so I take that vector at that angle, and let's start here. Let me pick another color real quick. And I start at 1, I maintain my angle of 45 degrees, and I come up 5 centimeters. So that represents a distance, a scale drawing distance of 250 miles. And then on the problem it says that you travel west, due west, for 150 miles. So let me pick another color. And we go due west, which is going to be straight along this line. And I level it up here. And 150, using my scale, should be about 3 centimeters long. So I come over 1, 2, 3 centimeters. I draw an arrow. And that represents my path, my flight, 150 miles. And you are asked to solve it both mathematically and graphically. Well, graphically is relatively straightforward. Your trip started here, it ended here, so you would draw this line, and you could determine that the trip was, and you measure the scale, So I'm coming up with about 7.5 centimeters. So we're looking at about 307 times 5 would be 35, 350, and with another 25, so maybe 375 miles. Okay, it's got to be less than the sum of these two numbers, which would be 400, and so maybe that's right. Now the graphical method isn't the best. It's prone to, I'm using magic markers here, and if my angle wasn't quite right, I would have some problems. And so the mathematical method of actually adding these together mathematically is the preferred method. And so we take the sum of our x's and the sum of our y's, and we resolve the vector that way. So we take this first vector, and it's 250 miles off northwest. So part of its path is going to be northward, and part of its path is going to be westward. The westward component is going to be equal to the distance times the cosine of our angle, and the northward component, distance north, is going to be equal to the distance times the sine of our angle. Now for us, fortunately, the angle is pretty straightforward. So if I knew the sine of 45, it's the same as the cosine of 45, which is like 0.707. So when you multiply, let's draw a little sketch down here. We don't have to do a scale model, we just have to do a sketch. The northern component, or the y component of our distance, is going to be our distance times the sine of 45. So that's 0.707 times 250. We come up with about 177 miles. So it travels 177 miles northward, and at the same time it travels the distance times the cosine of our angle, or an additional 177 miles westward. Then after that's finished, it adds to its trip another 150 miles westward. So if we take the sum of our y's, we get 177 plus nothing. So we've got 177 westward, or northward, sorry. And then the sum of both of those, so that's 177 plus 150, or 327. And so we go 327 miles west. And so the question still becomes, what is our resultant? And the resultant is going to be the hypotenuse. R squared is equal to a squared plus b squared. And so the resultant is going to be equal to the square root of a squared plus b squared. And so the resultant is going to be equal to the square root of 177 squared plus the 327 squared. And you square that, and then you add it to that, take the square root of it, and you get about 371 miles, which is pretty close to the 375 that we did with our diagram. Not exact, but pretty close. The angle can easily be found because the tangent, we've got two sides of a right triangle. The tangent of the angle is equal to opposite over adjacent. And so it depends on what angle we want, but if we want this angle here, for instance, this would be the opposite, this would be the adjacent. You take the inverse tangent of that, and that gives you the angle. So you can do that problem pretty quickly, too, by punching in actual numbers.